Welcome back to the channel, everyone. Today we are diving into one of the most important tools in calculus, the first derivative test for finding local extrema. Whether you are a student trying to master this concept or someone brushing up on your math skills, this video will help you understand how to identify local maxima and minima using the behavior of a function's derivative. Let us break it down step by step and make it as simple as possible. So suppose that you have a C, which is a critical point of a continuous function f, and that f is differentiable at every point in some interval containing that critical point, except possibly C itself. Then moving across the interval from left to right, if f prime changes from negative to positive at C, then we say that the function has a local minimum at that critical point. If f prime changes from positive to negative, that is when we see that we have a local maximum. And if there is no change in sign, then the function has no local extremum. So in this case, it has no local maximum and no local minimum at the critical point. Okay, so now let us use this example to really explain what we are trying to say. So first of all, we are given f of x to be equal to, so we have f of x, which is equal to s squared minus 3 then e to the x, and we are told to find the critical point. So remember from the previous video, to find a critical point, you first of all have to find the first derivative. So now, having two separate functions, we have to use the product rule. So for the product rule, we have the first one, and then we differentiate the second one, then plus we differentiate the first one, and we maintain the second part. So in this case, our f prime of x, now if we differentiate this e to the x, you get the same thing, plus s squared. Now if you differentiate s squared minus 3, you end up getting 2x, because negative 3 will give you 0, so you just have 2x left, and now you have e to the x. Remember, for your critical point to exist, it's when you equate your first derivative to 0 or where your first derivative is undefined. Now in this case, there is no x value that will make f prime of x undefined, so the only way is to equate it to 0. So you have s squared minus 3 e to the x plus 2x e to the x equal to 0. So you just have to factorize e to the x outside, and if you do so, you just have s squared then plus 2x then minus 3. So this is equal to 0. So basically, let me copy this one right here. So we just have to equate this to 0. So if we do that, we are going to get a first part equal to 0 and a second part also equal to 0. That is, we are going to have ex to the 0 and also s squared plus 2x minus 3 equal to 0. Now the question to ask is, whenever you have e to the x, can we have an x value that will make e to the x 0? No, we don't have such value. So over here, we have no critical point. There is no x value that will satisfy this equation right here. On the other hand, when we have s squared plus 2x minus 3, we can factorize this expression. If we do so, we can have this. So we can factorize by grouping, where we have the first two terms and the last two. So over here we have x minus 1, then plus 3x minus 1 equal to 0. So we have x plus 3x minus 1 equal to 0. So let's continue right here. So if we do that, we can see that x plus 3 equal to 0 means we have s equal to negative 3, and x minus 1 equal to 0 means we have x equal to 1. So the only critical point, so the critical point of our function, x is equal to -3 and x is equal to 1. Now the next part of the question is we have to identify the open intervals on which f is increasing and on which it is decreasing. To do that, we are going to need our critical point. So let's draw a number line. Always, whenever you have such a question, it's best to draw a number line to help you. So in this case, we have two critical points. So we have the smallest one being -3 and the bigger one being 1. And we have -infinity to infinity. So now, using over here, we want to pick a number which is between -infinity and -3. So we can select 0. So if we select 0, we are going to have, remember, we are going to evaluate at f prime. So f prime of 0, f prime is what we had over here. So f prime of 0, we are going to just have e to the 0, 0 squared plus 0 minus 3. So this is just e to the 0 is 1. Then we have minus 3 in the parentheses. So if you simplify, you have -3. So since we have a negative number, it means that all the numbers between -infinity and -3 goes down. Now let's move to -3 and 1. So from -3, so for 0, that is, we can select 0 is over here. So in that case, it means this goes down. From -infinity to -3, we can select -4. So in that case, we have e to -4, then -4 squared is 16. We are using this again. -4 squared is 16. Then 2 times -4 is -8. Then -3. Remember, so we are going to have 5e to the -4. And 5e to the -4 is approximately, we can have 0.018, which is positive. So in this case, this also goes up. And now we have to choose a number between 1 and infinity. So let's say we select 2. So in that case, we have e squared, then x squared. So in that case, we have 4 plus 4 minus 3. And that will give us 5e squared. So this is obviously positive. There's no need to even approximate. So since it is positive, this sign goes up. So now let's identify, is there a local maximum? Remember, to have a local maximum, f prime changes from positive to negative, right? So this is our critical point. So we have two critical points. We have -3 and we have 1. At 1, we can see that, let's start from -3. At -3, you can see that it changes sign from positive, it goes up, so meaning positive. So it changes sign from positive to negative over here. So since it changes from positive to negative, we can see that we have a local maximum. We have a local maximum. Remember, if it changes from positive to negative, we have a local maximum. So in this case, there is, so we can see there is a local maximum at x is equal to -3. How about 1? At 1, we can see that it goes down, so it changes from negative to positive right here. So since it's negative to positive, we can see that there is a local minimum. So there is a local minimum at x is equal to 1. Now, after checking the local max and local min, we have to check where the function is increasing and where it is decreasing, right? So using this, the function is increasing where the arrows are showing up. So we have -infinity, let me write it well, we have -infinity to -3, and also it increases between 1 and infinity, but it decreases from -3 to 1. I hope this is clear enough. Okay, Let's look at another example. So question 2, we have to do the same thing. So in this case, we have f of x is equal to x, then ln of x squared. So in this case, what do we do? First of all, find the critical point. And remember, in find the critical point, you have to first find the first derivative. So you differentiate this using the power rule. Using the product rule, you hold this in place, then you differentiate this, then you differentiate the first term, then you hold the second one in place. So what do we get if we differentiate ln of x all squared? Now remember, to differentiate this using the power rule, your 2 comes down. You have ln of x, then you differentiate what is inside the parenthesis. So if we differentiate ln of x, you have 1 over x. So you have this here. In this case, if we differentiate x here, you have 1. So if you multiply it by ln of x squared, you get the same thing. So we can simplify this by dividing this by that. So we just have our f prime of x in this case to be 2 ln of x plus ln of x all squared. Again, there is no s value that will make this undefined, so we just have to set this equal to 0. So f prime of x equal to 0 simply means we have 2 ln of x plus ln of x squared equal to 0. So what do you think we have to do over here? So over here, basically, all that you have to do is to factorize ln of x out. So if you factorize ln of x out, you have 2 over here, then plus ln of x. Remember, 2 times ln of x, you have this. And ln of x times ln of x, you have ln of x squared. So this is equal to 0. So this means ln of x is equal to 0, or 2 plus ln of x is equal to 0. So in that case, remember, to find x, we have to find the negative reciprocal of natural log. So as I said before, exponential and logarithm are inverses of each other, right? So what is the inverse of ln? That is exponential. So you can have this equal to e to the 0. Also, so e and ln will cancel each other, so you have x, and e to the power of 0 is 1. Over here, 2 plus ln of x, we can send 2 to the right hand side, becoming negative. And to find x, again, we do the same thing by introducing e. So we have x is equal to e to the power negative 2, which is the same as 1 over e squared. So our critical points, so we have 2 critical points. So critical points are x is equal to 1 and x is equal to 1 out of e squared. I hope this process is clear enough. Now afterwards, we have to check where the function is increasing and decreasing, and also if there is any local extremum. So again, let's draw our number line. Remember, to do that, you need your number line. So we have this. So first of all, you have between 1 and 1 over e squared. 1 over e squared is the least one, so we can have 1 over e squared over here. We have 1. But for a natural log of s, it is defined between 0 and infinity. Remember, natural log can't have a negative number, right? So it's between, over here is between 0 and infinity. So between 0 and infinity, we can select a number, and also what number can we select? So over here, we can select, remember, you are going to evaluate at f prime. We can select 1 over e cubed because it's less than 1 over e squared. You can also select 1 over e4 or 1 over e to the 5th. It's all the same thing. So now let's evaluate that. So to do that, our f prime is what we had over here. So we have 2 natural log of x. Now x in this case is 1 over e cubed, then plus ln of x, but x is 1 over e cubed, then all squared. So this will just simplify to, in this case, we have 2 ln 1 over e cubed can be written as -3, then plus over here we have ln e to the -3 all squared. So now, using the properties of logarithm, we can have -3 ln of e. Using the properties of logarithm, -3 will multiply 2, so we have -6 ln of e. Then we do the same thing over here. We have -3 ln of e all squared. And remember, ln of e is just 1. So in that case, we have -6 here plus. Now ln of e is also 1. So we just have -3 squared, which is +9. So we can see that this simplifies to +3. So it means that this is going upwards. Okay. Now let's select a number between 1 over e squared and 1. So 1 over e squared and 1, we can have 1 over e. So in that case, we have 2 ln 1 over e plus ln 1 over e all squared. So that simplifies to 2 ln of e minus 1. Then this also simplifies to ln e minus 1 all squared. And remember, the negative exponent will come down to multiply 2. So we have minus 2 ln e. Then over here, we are going to have the same thing. So minus over here, just ln e, then all squared. Now remember, ln of e is just 1. So we have minus 2 here. So we have -1. In this case, we're going to have -1. And -1 squared is +1. So this will simplify to -1. So clearly, you see that this also goes down. Now we are left with the last part. And the last part is we have to pick a number between 1 and infinity. So 1 infinity, we can pick e. Remember, e is approximately 2.7 something. So it definitely bigger than 1. The reason why I'm not picking whole numbers such as 2, 3, and 4 is because it's going to be very difficult to evaluate them. I'm choosing e because of natural log. Remember, they are inverses of each other, so it makes it very easy to simplify. So let's find f prime of e. F prime of e, in this case, you're going to have 2 ln of e, then plus ln of e all squared. Is this correct? So 2 ln of e plus here. So we know that ln of e is 1. So in this case, we have just 2. Over here, we have 1 squared, which is 1. So we have 3 over here. So we can see that this is going up. So now, where is the function increasing? So the function is increasing between 0 and 1 over e squared. So increasing, the function is increasing on 0 and 1 over e squared, and also increasing on 1 and infinity. Now, where is it decreasing? So the function is decreasing between 1 over e squared and 1. So decreasing on 1 over e squared, 1. Okay, so is there any local maximum and local minimum? Let's check. So for local maximum, f prime has to change from positive to negative. So over here, looking at the first critical point, we can see that it moves from positive, right? It goes up and it comes down right here. So then we can see that there is a local maximum at 1 over e squared. So there is a local max at x is equal to 1 over e squared, and there is a local mean at, now in this case, it goes down and it goes up. So we can say, so this one, it goes down before it goes up. So we can say at x is equal to 1, there is a local minimum. But what if, let's say over here, we had it going down? If we had something like this, will 1 still be a local minimum? What do you think? If, since this is going down and this is going down, remember, over here, if f prime does not change sign at c, then f has no local extremum. So if the signs are the same, in this case we have going down and going down, then it means that there is no local extremum. Just pay attention to that. Okay, now let's look at our third and last question. For the third question, we have f of x to be equal to cosine squared of x minus 2 cot of x, which is between 0 and pi. So just as before, we have to find f prime of x. So remember, if you differentiate cosine of squared x, how do you differentiate this? So to differentiate this, you have to use the chain rule. So let us do that right here. So let's say you have y equal to cosecant squared x. We can let u to be cosecant x. And now if we rewrite y, we are just replacing this with u. So we're going to have u squared. Now since u is a function of x, we can differentiate it with respect to x. And if you differentiate cosecant, you have negative cosecant x, then cotangent x. And now y is a function of u, so we can differentiate y with respect to u. So you have just 2u right here. So now your final answer for dy dx is dy du dot du dx. So this is basically 2u multiplying negative cosecant x and cotangent x. And now u is what we had over here. So our dy dx is minus 2 cosecant x multiplying cosecant x cotangent x. And remember, we can multiply this 2. So we have negative 2 cosecant squared x, then cotangent of x. So in this case, we have minus 2 cosecant squared of x, then cotangent of x. Or instead of using the chain rule, you can also use the power rule. Any of them works. You just have to be comfortable with any approach that you use and not to make any mistake. So in this case, if we differentiate this, we have this right here. So let's move on to the second term. For the second term, if we differentiate cotangent, you have cosecant squared x. So we just have to equate this to 0 because there is no x value that will make this undefined. So f prime of x equal to 0 simply means we have so this should be positive, because if we differentiate cotangent, you have negative cosecant squared. So we have negative 2 cosecant squared x cotangent x plus 2 cosecant squared x equal to 0. So clearly you see cosecant 2 cosecant squared is common in both terms, so we can factorize it out. So if we do so, we just have negative we have negative cotangent x. In the last term, we just have positive 1 equal to 0. So we have 2 cosecant squared x to be equal to 0, or we have that second term, which is 1 minus cotangent x to be equal to 0. Now, remember, cosecant squared is the same as, or cosecant itself is just 1 over sine of x. So even if we equate 1 over sine squared x equal to 0, this will just give you 1 over 0, which give you no critical point. So there is no critical point in this area. Now we can have 1 equal to, if we send cotangent to the right hand side, we have this. And now cotangent is the same as cos x over sine x. Now this is equal to 1. So basically we have cosine of x is equal to sine of x. So what x values will satisfy this? Using the reference angles that we did before, remember the only x value that will satisfy this is when you have x to be equal to pi over 4, because sine pi over 4 is 1 over 2. Then we also have cos pi over 4. So you really have to check that to see if indeed you get the same thing, right? So sorry, sine pi over 4 is root 2 over 2, and cos pi over 4 is also root 2 over 2. So that's the only x value. But remember, since we are dealing with infinitely many terms, you should add just n pi, because pi over 4 plus n pi is going to satisfy this, where n is an integer. But note that you were given a condition, x should be between 0 and pi. So we have to choose. If n is positive 1, you have pi over 4 plus pi, which is bigger than this pi right here. So it means we can't have this. And if it is negative 1, we are going to have pi over 4 minus pi, which will also exceed 0. So we can't also have this. So the only critical point that will satisfy the condition, so the only critical point is when x is equal to pi over 4, because pi over 4 is definitely between 0 and pi, so we can have that. So now we have to draw our number line again. So using the critical point that we got, so we had pi over 4 here. Remember, this is to the range given was between 0 and pi, so this is from 0 to pi. So we have to find f prime. Now between 0 and pi, which one can we use, right? So we can pick pi over 6. So between 0 and pi over 4, there is pi over 6 somewhere here. So now let's evaluate this. If we do so, f prime, we had f prime to be this. We had f prime to be this right here, so we can use that. So we have 2 cosecant squared x, so which is pi out of 6. Then 1 minus cotangent of x, which is pi over 6. So let's simplify that. If we do so, we are going to have 2. Now remember, cosecant squared is 1 over sine squared. So you have 1 over sine squared pi out of 6. Then you have 1 minus cotangent is cosine over sine. So you have 2. Then sine of pi over 6 is basically 1. Sine of pi over 6, which is just sine of 30, is 1/2. So if you square it, you have 1 out of, then 1 over 4. That is if you square it. You have to multiply by 1 minus. Now cos of pi over 6 is root 3 over 2. And sine of pi over 6, as we know already, is 1 out of 2. So if you simplify this, you're going to get 2. Now 1 over 4 dividing 1 over 4 is basically 4. Then if you simplify this whole thing, you're going to get 1 minus root 3. So this is equal to 8 multiplying 1 minus root 3. So if you expand, you have 8 minus 8 root 3. Remember, 8 root 3 is bigger than 8. So if you subtract 8 root 3 from 8, you should get a number that is less than 0. So it means that this part is going down. I hope this is clear. For a number between pi over 4 and pi, we can choose pi over 2. So let's go ahead to evaluate pi over 2. So in this case, we have 2 cosecant squared x. So our x is pi over 2 now. So we have pi over 2, then 1 minus cot pi over 2. So cosecant squared is just 1 over sine squared. Now our angle is pi over 2. We have 1 minus cosine of pi over 2 out of sine of pi out of 2. So this will just simplify to. Now, first of all, to find sine squared pi over 2, you have to find sine of pi over 2. And sine of pi over 2 is 1. So 1 squared is still 1. Cos of pi over 2 is 0. So in this case, you just have 0 out of, now sine pi over 2 is 1. So you just have 1 here. So if we simplify this, you just have 2 multiplying 1 times 1, because 0 minus 1 over here is 0. So this simplifies to 2. So clearly we can see that this goes up. So our f is increasing on pi over 4 and pi. And f is decreasing on between 0 and pi over 4. That's where it is decreasing. So we have 0 and pi over 4. Now, also, is there any local max or is there a local min? So looking at this, we can see that at the only critical point that we have, which is pi over 4, the sign changes from negative to positive. So since it does that, it means we have a local minimum. So we have a local minimum at x is equal to pi over 4. I hope this really explains the concept of what we did today, which is first derivative test for local extrema. Now, if you have any questions, just let me know in the comment section. So that is it for today's lesson on the first derivative test. I hope this video gave you a clear understanding of how to use derivatives to identify local extrema. If you found this helpful, don't forget to like, share, and subscribe to the channel for more calculus content. And if you have any questions or topics you would like me to cover, drop them in the comments below. Keep exploring, stay curious, and I'll see you in the next video. Bye.